Imagine this. When Maxwell first predicted the existence of electromagnetic waves, the only ones we actually knew about were visible light waves. That's it, just the rainbow colors our eyes can see. But soon after, scientists began discovering new regions, ultraviolet and infrared first, and later X-rays and gamma rays by the end of the 19th century. Today, we know the electromagnetic spectrum is huge. It covers everything from radio waves that bring you FM music to X-rays at the hospital and even gamma rays from nuclear reactions in space. All of these are just different forms of the same family, electromagnetic waves. Now let's talk numbers. The electromagnetic spectrum spans an enormous range. Frequencies go all the way from 10 superscript 3 Hz to 10 superscript 2 superscript 3 Hz. The corresponding wavelengths range from 10 meters, that's longer than a football field, down to 10 superscript 1 meters, smaller than the size of an atomic nucleus. And here's the golden relation that ties them together: C is equal to nu lambda. That means speed of light equals frequency multiplied by wavelength. So if one goes up, the other must come down. This simple relation holds for every electromagnetic wave, no matter where it lies on the spectrum. Out of this gigantic spectrum, our human eyes are sensitive to just a tiny sliver, the visible region. This spans from about 400 nanometers for violet light to about 700 nanometers for red light. The frequency range is roughly 4 times 10 superscript 1 Hz to 7.5 times 10 superscript 1 Hz. In this band, violet has the highest frequency and red has the lowest. The colors follow the familiar rainbow order: violet, blue, green, yellow, orange, red. Think about it, the entire beauty of sunsets, rainbows, and even what you're seeing right now on your screen comes from just this narrow window of the spectrum. Now, if we move to higher frequencies than violet, we get ultraviolet radiation, X-rays, and finally gamma rays. Ultraviolet spans from about 10 nanometers to 400 nanometers. X-rays shrink further down to 0.01 nanometers to 10 nanometers. And gamma rays? Less than 0.01 nanometers, the most energetic waves we know. The energy of these waves is linked to frequency by the formula E is equal to h nu, where h is Planck's constant. That means higher frequency always means higher photon energy. Gamma rays pack such a punch that they can come from nuclear reactions or exploding stars, a real powerhouse of nature. On the opposite side, we have the low-frequency giants. Infrared waves stretch from 700 nanometers to about 1 millimeter. They are famous for thermal imaging and the remote control you use for your TV. Microwaves, with wavelengths from 1 millimeter to 1 meter, are used in radar, ovens, and communication. Go even lower, and you hit the domain of radio waves with wavelengths longer than a meter. AM, FM, television, even long radio waves spanning thousands of meters all belong here. These low-frequency waves may not carry much energy, but they travel long distances, making them perfect for communication. So let's tie it all together. The electromagnetic spectrum is like a grand orchestra of waves stretching from the tiniest gamma rays to the longest radio waves. There's no sharp boundary between them, each region just fades into the next. The relation C equals nu times lambda binds them all together. And remember, visible light is just a small slice in this vast range, yet it's the only part our eyes can detect. The rest of the spectrum is revealed to us through science and technology, from X-ray machines to microwave ovens to space telescopes. The big idea? Maxwell's theory didn't just give us light, it gave us the key to understanding the entire electromagnetic spectrum, unifying what once looked like completely different phenomena into one elegant framework.